Hello, welcome to part 3 of this series of lessons on the moment of a force or torque. I'm assuming you've seen and understood parts 1 and 2. Part 2 was split into 2 separate videos. In part 3 we're going to briefly look at the units we use for measuring moment. Then we're going to look at this equation. Moment is Fdsin theta. We're going to use the equation to do some problem solving. Finally, to complete the picture, I'd briefly like to mention a couple of slightly more advanced concepts, couples, and the fact that moments can be considered as vectors. As we work through, there are exercises for you, so you will want a pen, paper and calculator to get the most out of it. If you need to pause, now is a good time. Let's talk briefly about units. You should already know that the SI unit for moment is the Newton meter, capital N, small m. But other units are possible. And you will find, for example, engineers often use pound feet. So you can multiply any force unit by any distance unit, and it's a moment. And you have to use a bit of common sense dealing with calculations involving those units. I'm not going to say any more about them. What I will mention though is this, that a Newton meter is actually an ambiguous unit. It can mean two different things. It's used both for moment and also for work. Now I hope you've met the idea of work or work done already. Let's briefly talk about it. Here's a force, there's a point, let's draw the line of action, let's give you the distance from the point to the line of action. There's no problem working out the moment. It's force times that distance, 20 newtons times 3 meters is 60 newton meters. No surprises. But here's another situation. Let's apply a 20 newton force to an object, and maybe that's the only force on the object. It will cause the object to accelerate. Suppose it accelerates over a distance of 3 meters while the force is applied. To calculate the work done by the force, which means the amount of energy transferred to the object, you probably know that the work done is given by force times distance. Well, it's 20 newtons times 3 meters. It's 60 newton meters. It looks the same as the top equation, but they mean totally different things. This 60 newton meters at the top means the turning effect, the moment or torque. This 60 newton meters means the amount of energy transferred. It would be the amount of kinetic energy that the object has acquired in this example. So newton meters is a unit with two different meanings. Usually if you see it, it will be pretty obvious if we're talking about torque or talking about work. And usually work done or energy is given in joules. So instead of writing 60 newton meters, it would be more usual to write joules. But be aware, the newton meter has two different meanings. Let's move on to the main part of the lesson. We'll start with a problem solving exercise for you. Here's a rod bar. Let's suppose its length d is 2 meters. Let's call the top point P, and let's apply force to the bottom of 30 newtons. Line of action of the force is there. Let's put the angle in so you know what the direction of the force relative to the rod is. 50 degrees. The exercise for you is very simple. Find the moment of the force about point P. Pause and have a go. Well, I hope you've tried it. The key method is to find the distance, a perpendicular distance from point P to the line of action. Let's draw it in. I've called it L, and it's perpendicular to the line of action. Now it's worth knowing that this distance L, the perpendicular distance from the point where we're taking moments about to the line of action, has got some names. It can be called the lever arm, or sometimes it's called the moment arm. So if you ever see those phrases, lever arm or moment arm, it's simply referring to this perpendicular distance. And to work out the moment of the force about P, we're going to multiply F, 30 newtons, by this length. So the problem is, how do we work out this length L? Well, if you look, we have a right angle triangle. The sine of angle 50 is the opposite side, which is L, divided by the hypotenuse, which is D. Let's write that down. Sine 50 is L over D, opposite over hypotenuse. So to get L, we have to rearrange it, and that will give L is D sine 50. Now it's easy to find the moment. The moment is the force times the lever arm. It will be force times, well, L is D sine 50. Stick the values in, and it comes to 46 Newton meters clockwise. Now, I hope that makes sense. Take a look at that. It's an important calculation. Let's talk about this formula. The moment is Fd sine theta. We've just used it basically, but let's go over what's going on. Let's suppose we want to find the moment of force F about some point P. Let's draw force. Let's draw point P down here. How do we do it? Well, let's suppose Q is a point somewhere on the force's line of action. So we draw the line of action. I need a point Q. It could be anywhere. It could be down the bottom here. It could be the tip of the arrow, in the middle of the arrow, at the tail, up here. Point Q could be anywhere. Let's mark a point Q up here. And let's suppose in the question we are given, so we know the distance PQ. So we know the distance from the point about which we are taking moments to some point on the line of action. We know it's distance D. Let's mark it. We know this distance D. Let's suppose we also are told, so we know the angle between the line of action and PQ. So we know the angle between this line and the line of action. Let's mark it in, theta. So we know three things: the force magnitude, this distance from the point where we're taking moments about to some point on the line of action. We know the angle between that line PQ and the line of action. How do we work out Fd sine theta? Well, if you want to pause, you could try deriving it for yourself. So pause and have a go. Well, the calculation, the derivation I should say, is very similar to the calculation we did on the previous slide. Let's draw in the perpendicular, the lever arm, the line joining P to the line of action, so it's at 90 degrees to the line of action. That's L. Of course, the moment is simply F times L. But we know that sine theta is L over D. Right angle triangle. Sine theta is the opposite, L over the hypotenuse D. Sine theta is L over D, so L is D times sine theta. The moment is F times L, so we substitute for L and get that the moment is Fd sine theta. That's the proof of the formula, if you like. Now, can we use the formula? Let's have a go. Oh, before we do, I'd like to mention this. It's a useful point. Suppose theta is 90 degrees. Then sine theta is sine 90. And you ought to know that sine 90 is 1. That means this formula would become Fd sine of 90. That would be Fd times 1. It would just be Fd. So if the angle theta is 90 degrees, we get our basic formula. Moment is force times this. Let's just draw that. It means that if point P is here and point Q is up here, so that we get an angle of 90 degrees, if theta is 90 degrees, then it's a simple situation where Fd sine theta would be Fd times sine 90. And that would simply leave us with force times this distance, if theta is 90 degrees. Now, a very simple exercise for you. Can you apply the formula? I hope you can remember it. Moment is Fd sine theta. To this problem, what is the moment of F about point P? Pause and try that one. Well, it's simply a case of putting the numbers in. Let me mark Q for you, a point on the line of action, Q. There's the formula. We know the force 40, we know the distance PQ is 2.5 meters, and the angle between PQ and the line of action is 55 degrees. So all we have to do is say 40 times 2.5 times sine 55. It comes to 82 Newton meters clockwise, roughly. Does it matter which angle we use? We could use this bigger angle here. Let me mark it in green. What happens? Well, how big is it? You ought to know that the angle marked in green is simply 180 minus 55, which is 125. If you don't already know, let me tell you, sine 55 is the same as sine 125. The sine of an angle is the same as the sine of 180 minus that angle. And in fact, if we did the calculation using sine 125, it would give exactly the same answer. So we could use either the big angle, the obtuse angle, or the smaller angle, the acute angle. It makes no difference to the calculation. Now, here's a slightly harder set of small exercises for you. Here's a side view of a block. It's 40 centimeters high, it's 30 centimeters across. I'm going to apply a force to the corner, as shown, 12 newtons, at 60 degrees to side BC, 60 degrees to the vertical. And I want you to do 4 calculations basically. Can you find the moments of the 12 Newton force? First, what's the moment about point A? What's the moment of the force about point B? What's the moment about point C? And lastly, what is the moment of the force about point D? 4 separate calculations. Pause and have a go. Let's go through these. Let's put the line of action in. Let's do the moment about A first. Well, from A to a point on the line of action takes us from A to B. That's the key distance here. Let's draw it with a yellow line. You will note the angle between this line AB and the line of action is 30 degrees. 60 and another 90 make 150. If we take off 150 from 180, it leaves us with 30 degrees here. 60 degrees is not the angle we need. We need the angle between the line of action and this line AB, joining the point we're taking moments about to a point on the line of action. That's a critical angle, 30 degrees, not 60. So what is the moment of the force about point A? Well, we put the numbers into the equation. The force is 12, the distance is 30 centimeters, AB is 30 centimeters long, so it's 0.3 meters. We multiply by sine 30, not by sine 60, because that is a relevant angle. And it will give 1.8 Newton meters. Don't forget that's a clockwise rotation. Okay, what's the moment of the force about point B? Well, there's no calculation needed. The line of action passes through point B, therefore there is no moment. The distance from the point to the line of action is 0 because the line of action passes through the point. So whenever you have a force whose line of action goes through a point, the moment about that point is 0. Let's do the moment about point C. There's a point we're taking moments about, C. The point on the line of action is B. So that yellow line is the one we need the length of. It's 40 centimeters. The angle we need is the angle between BC and the line of action. So this time it is 60 degrees. So the moment of the force about point C is 12 newtons times 0.4 meters times sine of 60. Comes to 4.2 Newton meters clockwise. Now the last one, the moment about point D, is harder. Let's start by drawing the line joining the point about which we're taking moments to a point on the line of action. So we're going to join DB. And we need the length of dB. How do we find the length? Well, we can use Pythagoras. We have a right-angled triangle here. So we can say the hypotenuse squared, which is dB squared, is 30 squared plus 40 squared. That will give us dB is root 2500, dB is 50 centimeters. And if you're sharp, you will have noticed that there's no calculation actually needed. This is a 3, 4, 5 triangle. 30, 40, therefore 50. The ratio of the sides is 3 to 4 to 5. 30, 40, 50. So you could have got away with simply stating dB is 50 centimeters. So we know the length dB. Do we know this angle? Well, it looks a bit like 90 degrees, but it isn't. You can't assume it's 90. We need to work out this small angle at the top and add it to 60. Let's see if we can work out the small angle at the top. It's angle DBC. And I hope you know from your trigonometry that the tangent of an angle is the opposite over the adjacent. So we can say that the tangent of angle DBC is 30 over 40, 0.75. So DBC, the angle is inverse tangent arctan, or tan minus 1, of 0.75. On your calculator it comes to 36.9 degrees. So actually this angle here is 60 plus 36.9. Let's work out the moment. Well, the force is 12 newtons. The distance we've worked out, dB, 0.5 meters, 50 centimeters, 0.5 meters. And we're going to take the sine of the angle, and that angle is 60 plus this smaller angle. It's 60 plus 36.9. So we'll end up with 12 times 0.5 times sine of 96.9. 596, round it to one or two significant figures, 6.0 Newton meters clockwise. That's quite a hard one. And the last exercise I shall ask you to do is a typical simple exam question. Let's suppose we have a uniform horizontal 30 kilogram beam in equilibrium. It's just being held there. Its length is 2.4 meters. It's pivoted at one end, P, and it's supported by a steel cable at the other end as shown. So the steel cable is at an angle. It's at an angle of 51 degrees to the vertical, supporting the right hand end of the steel beam. So the question is, what is the tension in the cable? What force is pulling, supporting the beam? G is 9.81 meters per second squared. Pause, see if you can solve that for yourself. Okay, let's go through it. This really is an example of using the principle of moments. We're going to take moments about point P. We're going to balance the clockwise moment produced by the weight with the anti-clockwise moment produced by the tension in the cable. Let's work out an expression for the moment produced by the tension. Oh, let's mark the other forces in first. Weight is through the middle because it's a uniform beam. 1.2 meters, 1.2 meters. Line of action of the force is there. Okay, what is the moment that the tension produces this force about point P? Well, we use our Fdsin theta formula. Can you see what the values will be? Instead of F, we're going to write the letter T. Instead of D, we're going to use this distance, the point about which we're taking moments, to a point on the line of action. And the angle has got to be the angle between this yellow line and the line of action of the force. Hope you can see it's 51 plus 90. That's the full angle. So it's sine of 90 plus 51. If we simplify that a bit, we can write it as 2.4t sine 141. Now we're ready to use... by the way, I could have worked that angle out 39 degrees. I could have said 2.4t sine 39. It's exactly the same thing. Now we're going to use our principle of moments. Taking moments about p, we can say that the clockwise moment will equal the anti-clockwise moment because the thing is in equilibrium. What's a clockwise moment? It's the moment produced by the weight. It's this force times this distance. No funny angles, it's a 90-degree angle. So the clockwise moment is going to be 30 times 9.81, m mass times g. So weight downwards times 1.2, the distance. That will equal the anti-clockwise moment produced by the tension. It will equal 2.4t sine 141. There we've got an equation. We need to simplify it and solve for t. And if you work through the arithmetic, you get 234 newtons. You'll note all the data in the question was given to 3 significant figures, so it makes sense to give the answer to 3 significant figures. Okay, I hope that makes sense. Now, to finish off, I'd like to say a few words about, first of all, couples, and then we'll talk about moments as vectors. This is a slightly more advanced subject, and you may or may not need to know it. I'll go through it quickly. What is a couple? Well, in physics and mechanics and engineering, a couple, the word has got a special meaning. A couple is a pair of equal magnitude forces with opposite directions and different lines of action. Let's draw that to make sure we understand what it means. So we've got a force, call it A, and got another force of the same magnitude, the same size, but the opposite direction. And they have different lines of action, so there's a gap between their lines of action. That pair of forces satisfying these conditions, the pair of forces is called a couple. Using the suitable notation, we could say A equals minus B. The minus sign tells us that the directions are opposite. I suppose I should really have these overlined or little arrows over the top or underlined to show their vectors. A and B are vectors, and A is minus B. What's so interesting about a couple? Well, it turns out that the moment produced by a couple is the same whatever point you choose, which is quite surprising. The moment normally depends on the distance from the force, but it turns out that the moment of a couple is the same about any point, and I'll quickly demonstrate why. There's our two forces, two equal forces in fact, so the magnitude of the top and bottom force are the same. I've called one F and the other F. Those are the magnitudes. Here's a point P. Let's suppose the lines of action of the two forces are separated by a distance d. How do we work out the moment of the couple about this point? Well, what we're going to have to do is work out the moment of each force about the point and add the two moments. Let's put some distances in. This is d, separation. Let's suppose that this point is a distance a from the upper force. A perpendicular distance is a. What's the moment of the couple about point P? Well, it's this. We've got the bottom force first. We multiply the force, F, by the distance to point P. Well, that distance is d plus a. So it's F into d plus a. And because it's clockwise, I'm calling it positive. The other force, the top force, is producing a moment which is anti-clockwise about P. And the sign of the moment is F times A. So we're going to say from the bottom force we've got that moment, and then from the top force we've got minus FA moment. Expand that, FD plus FA minus FA, the FA terms cancel, and we're left with FD. So it doesn't matter where P is, we could put it anywhere at all, and you'd always get the same answer, which is F times D. And that is the magnitude of either force times the separation between the lines of action. And if you want, you can prove for yourself that even if you pick a point in between the two forces, this is still true. You could pick a point 1,000,000 light years away, and the moment of the force about that point would be F times D, the force times the separation. The other thing I'd like to mention briefly is that moments are, technically speaking, a type of vector. Won't go into the details, but they are a type of vector. So you have to think in 3D really. If we have a force acting to the right like this, it has some moment about point P. The actual vector representation of the moment is a vector coming out of the screen towards you, pointing directly at you. So you have to think in 3 dimensions. The moment of F about P is a vector through P out of the screen towards you. To make that a bit easier to understand, let's draw some 3-dimensional coordinates, x, y and z axes. Let's suppose force, I've underlined it to remind you it's a vector, force F acts parallel to the x-axis and the line of action of the force is in the xy plane. Now the lever arm, suppose we want the moment about the origin. The lever arm is from the origin to this point here, which is going to give you a line perpendicular to the line of action. We can draw a vector from the origin to that point. That's a type of vector called a position vector. So we've got a force, we've got a position vector, which is the lever arm basically. And how do we show the moment of the force F about the origin? Well, it's a vector along the z-axis. And if you're going to study moments at a high level or learn some mathematics, some vectors, this is something you'll have to learn to deal with. In mathematical terminology, the moment of this force about the origin is the vector product or cross product of r and f. Moment is r cross f. Now if that doesn't mean anything to you, don't worry about it. You may or may not learn it later on. Okay, I mentioned the last bit simply as a stepping stone if you're going to do the more advanced work. But thank you for watching these lessons on the moment of a force. I hope they've helped you.